So here you are, lying in the dark, and it's quiet. Or at least, you think it's quiet. But if you really listen, and I mean really listen, there's always something. Maybe it's the hum of an appliance somewhere in your home, or the distant wash of traffic, or the soft rhythm of your own breathing. Even in the quietest room you've ever been in, if you hold perfectly still, you might catch the faint thud of your own heartbeat, the rush of blood in your ears. Silence, true silence, is almost impossible to find on this planet. And that fact alone tells you something remarkable about the world you live in. It is absolutely saturated with sound all the time, everywhere. And the machinery your body uses to detect it is so absurdly sensitive that it can pick up vibrations smaller than the diameter of an atom. Let that sit for a second. Smaller than an atom. Your ear can do that. We'll get to how, eventually. But for now, just know that the story of sound, how it works, how we figured out what it is, how we learned to capture it and shape it and send it across the world, is one of the most fascinating threads in all of science and engineering. And it starts, like a lot of great stories, with people getting it completely wrong. For most of human history, nobody had any real idea what sound was. I mean, people obviously knew what sound did. You bang a drum, you hear a noise. Someone shouts across a valley, the words reach you a moment later. But the question of what was actually traveling through the air between the drum and your ear, or between the shouter and the listener, that was genuinely mysterious. And the answers people came up with were, well, creative. The ancient Greeks were the first to really sit down and think about this in a systematic way. And honestly, they got surprisingly far, considering they had no instruments, no way to slow things down or measure them precisely. Pythagoras, yes, the triangle guy, was probably the first person in the Western tradition to connect sound to mathematics in a rigorous way. This would have been around the 6th century BC, so we're talking roughly 2,600 years ago. And the story goes like this. Pythagoras was walking past a blacksmith's shop one day, and he noticed that the hammers striking the anvils produced different musical tones. Some hammers made higher sounds, some made lower sounds, and Pythagoras, being Pythagoras, didn't just walk on by. He stopped, he listened, and then he went and weighed the hammers. Now, the specific details of this story are almost certainly embellished. Historians have picked it apart pretty thoroughly, and the physics of hammers hitting anvils doesn't actually work out the way the legend says. But here's what matters. The core insight that Pythagoras and his followers developed from this kind of investigation was absolutely real, and it was revolutionary. They figured out that musical harmony, the thing that makes certain combinations of notes sound pleasing and others sound terrible, is governed by simple numerical ratios. If you take a string and pluck it, you get a note. If you press the string down at exactly the halfway point and pluck the shorter half, you get a note that's exactly 1 octave higher. The ratio is 2-to-1. If you divide the string into thirds and pluck 2/3 of it, you get what musicians call a perfect fifth, the interval between the first and fifth notes of a scale. The ratio is 3-to-2. These aren't arbitrary. They're baked into the physics of vibrating objects, and Pythagoras and his school discovered them with nothing more than a single-stringed instrument called a monochord and an obsessive love of numbers. Think about what that means. 2,600 years ago, someone realized that beauty, the specific, undeniable beauty of musical harmony, has a mathematical structure, that the difference between a chord that makes you feel something and a random collection of noise is a matter of simple fractions, That's extraordinary. And it set the stage for everything that came after, because it established this fundamental idea that sound isn't magic. It isn't the voice of the gods. It's something that follows rules that humans can discover and describe. But knowing that vibrating strings produce tones governed by ratios is not the same as knowing what sound actually is. The Pythagoreans didn't really have a theory of sound propagation. They didn't explain how the sound gets from the string to your ear. For that, we need to jump forward a couple of centuries to Aristotle, who was born in 384 BC and who had opinions about literally everything. Aristotle proposed that sound was a disturbance in the air, that when something vibrated, it pushed the air next to it, and that push traveled outward, kind of like ripples in a pond. He wasn't exactly right about the details, but the basic metaphor, sound as a wave moving through a medium, was a genuinely brilliant intuition. He also correctly noted that sound needed something to travel through. He argued that in a void, a vacuum, there would be no sound, because there would be nothing to carry the disturbance, and that turns out to be exactly correct, though it would take about 2,000 years before anyone could actually test it. Here's the thing about the ancient understanding of sound, though. It was philosophical. It was qualitative. People could say, sound is a disturbance in the air, and harmony involves simple ratios. But they couldn't measure the speed of sound. They couldn't explain why different instruments sound different even when they play the same note. They couldn't describe the shape of a sound wave or calculate its frequency. All of that required tools and mathematical frameworks that simply didn't exist yet. So, for a very long time, through the Roman period, through the Middle Ages, through centuries of human civilization, the understanding of sound basically stayed where the Greeks left it. There were contributions from Islamic scholars during the medieval period, people like Al-Farabi in the 10th century, who wrote extensively about music theory and acoustics. But the fundamental physics didn't advance much until the scientific revolution kicked into gear in Europe in the 1600s. And this is where things start to get really fun, because the 17th century was when people started actually doing experiments with sound, and the results were wild. Let's talk about one of the most famous early experiments. In 1654, a German scientist and politician named Otto von Guericke. He was actually the mayor of Magdeburg, which is a delightful detail, demonstrated something that shocked the world. He had invented an air pump, one of the first devices that could create a partial vacuum, and he used it for dramatic public demonstrations. The most famous one involved two large copper hemispheres that were placed together and then had the air pumped out from between them. Two teams of horses, pulling in opposite directions, couldn't pull the hemispheres apart. The atmospheric pressure holding them together was that strong. But von Guericke also did something quieter and, for our purposes, more interesting. He put a bell inside a glass jar and pumped out the air, and as the air was removed, the sound of the bell got fainter and fainter until, in the near vacuum, you could see the clapper striking the bell but hear almost nothing. Aristotle had predicted this 2,000 years earlier, just by thinking about it. Now, here was experimental proof. Sound needs a medium. Take away the air, and you take away the sound. Robert Boyle in England repeated and refined this experiment in 1660 with a better vacuum pump, and the result was the same. A ticking watch inside an evacuated glass vessel went silent. You could see the mechanism moving, but the sound couldn't reach you. It's one of those beautiful moments in science where an ancient philosophical argument gets confirmed by a physical demonstration, and suddenly the idea moves from probably true to definitely true. So by the mid-1600s, the scientific community had established a few key facts. Sound is produced by vibrating objects. It travels as some kind of disturbance through air or other materials. It cannot travel through a vacuum. And musical tones are related to the frequency of vibration in simple mathematical ways. That's a solid foundation. But the next question, and this is the one that really opens up the whole field, is how fast does it travel? People had tried to figure this out before, with varying degrees of success. The first serious attempt is usually credited to Marin Mersenne, a French friar and mathematician who, in 1636, published a book called Harmonie Universelle. Mersenne was a fascinating character. He was a monk, a theologian, and also a hardcore scientist who corresponded with basically every major thinker in Europe, including Descartes, Galileo, and Pascal. He was like the 17th century internet, connecting people and ideas across borders. And among his many contributions, he tried to measure the speed of sound by timing the delay between seeing a cannon fire and hearing the boom. His method was simple. Stand a known distance from a cannon, watch for the flash, start counting. When you hear the sound, stop. Calculate the speed. He came up with a value of around 450 meters per second, which is too high. The actual speed of sound in air at room temperature is about 343 meters per second. But for a first attempt with no precision instruments, it wasn't bad. The error came mostly from the difficulty of timing short intervals accurately by hand. You're essentially trying to measure a delay of a few seconds over a distance of a kilometer or two, and human reaction time introduces significant uncertainty. But Mersenne established the method, and over the following decades, other scientists refined it. In 1709, William Derham, an English clergyman and naturalist, conducted a much more careful version of the experiment. He stood in the tower of the Church of St. Lawrence in Upminster, which is now part of Greater London, and watched for the flash of cannons fired from various locations at known distances. By averaging many observations and carefully accounting for wind, he arrived at a speed of about 348 meters per second, which is remarkably close to the modern accepted value. Think about that. A man standing in a church tower in 1709, watching distant cannons flash, clicking a pocket watch, and he nailed the speed of sound to within about 1.5%. That's beautiful science. Now, measuring the speed of sound is interesting in its own right, but what it really does is give you a crucial piece of the puzzle. Because once you know the speed and you know the frequency of a sound, how many vibrations per second, you can calculate the wavelength, which is the physical distance between one wave crest and the next. Speed equals frequency times wavelength. That simple equation connects the abstract musical world of Pythagoras to the physical world of waves moving through air. A concert A, the note orchestra's tuned to, vibrates at 440 times per second, 440 hertz in modern units. The speed of sound is about 343 meters per second, so the wavelength of that note is 343 divided by 440, which works out to about 78 centimeters. That's roughly the length of your arm. Every time you hear that note, the air pressure is rising and falling in a pattern that repeats every 78 centimeters between you and the source. There's something wonderfully tangible about that, isn't there? Sound isn't some ghostly abstraction. It's a physical pattern in the air with a real, measurable size. And this is where we start to understand something deeper about what sound really is, at a mechanical level. When you pluck a guitar string, the string moves back and forth very quickly. As it moves in one direction, It pushes the air molecules next to it closer together, creating a tiny region of higher pressure. Then, as the string swings back the other way, it pulls back, creating a tiny region of lower pressure. That high pressure zone pushes on the air molecules next to it, which push on the ones next to them, and so on, and the disturbance ripples outward in all directions, like an expanding sphere. The air molecules themselves don't travel from the guitar to your ear. They just jostle back and forth in place, each one bumping into its neighbor. It's the pattern, the wave, that travels. The individual molecules barely move at all. Here's a nice way to picture it. Imagine you're at a stadium, and the crowd does the wave. You know, where everyone stands up and sits down in sequence, so it looks like a wave rolling around the stadium. Nobody actually leaves their seat. Each person just stands briefly and sits back down. But the wave itself travels all the way around. Sound works the same way. The air molecules are the people in the seats. The pressure disturbance is the wave rolling through. And just like the stadium wave, the speed of the wave has nothing to do with how fast any individual person moves. It depends on how quickly the signal passes from one person to the next. This type of wave, where the motion of the individual particles is back and forth in the same direction the wave is traveling, is called a longitudinal wave. It's different from, say, a wave on a rope, where you flick the rope up and down, but the wave travels sideways along its length. That's a transverse wave. Sound in air is longitudinal. Compression, rarefaction, rippling outward. And the speed at which that pattern propagates depends on two things: how dense the medium is, and how stiff or springy it is. Air is not very dense and not very stiff, so sound moves through it at a moderate pace. 343 meters per second, which is about 767 miles per hour. That's fast in everyday terms, but compared to light, which travels at about 300 million meters per second, it's practically standing still. That's why you see lightning before you hear thunder, and why you can estimate how far away a storm is by counting the seconds between the flash and the boom, roughly 1 mile for every 5 seconds, or 1 kilometer for every 3. But here's what's interesting. Sound doesn't just travel through air. It travels through water, through steel, through wood, through bone, through almost anything that has molecules that can bump into each other. And it travels at different speeds in different materials. In water, sound moves at about 1,480 meters per second, more than 4 times faster than in air. In steel, it's even faster, around 5,960 meters per second. The denser and stiffer the material, generally, the faster sound travels through it. This fact has enormous practical consequences, and engineers have exploited it in ways that affect your life every single day, from the sonar systems that map the ocean floor to the ultrasound images that let expectant parents see their baby for the first time. But those are stories for later. Right now, let's stay in the 17th century for a bit longer, because there's a person we need to talk about. Someone whose work on sound and waves was so far ahead of its time that it took decades for the rest of the world to catch up. His name was Christian Huygens. He was Dutch, and he was born in 1629 into a wealthy and well-connected family. His father was a diplomat and a friend of René Descartes. Huygens was one of those rare intellects who seemed to excel at everything he touched. He built some of the best telescopes of his era, discovered Titan, the largest moon of Saturn, invented the pendulum clock, and made foundational contributions to probability theory. But for our story, what matters most is his work on waves. Because Huygens developed a principle that changed everything about how we understand the way waves move through the world. It's called Huygens' principle, and it's one of those ideas that sounds almost too simple at first, but the more you sit with it, the more powerful it becomes. Here's the basic idea. Imagine a wave, any wave, moving through space. A sound wave, a ripple on a pond, a pulse of light, whatever. At any given moment, that wave has a wavefront, which is just the leading edge of the disturbance. Think of it like the crest of a wave rolling toward a beach. Now, Huygens said something really elegant. He said that every single point along that wavefront can be thought of as a tiny new source of its own little spherical wave. Each point sends out its own miniature ripple, expanding outward in all directions. And the new position of the overall wavefront a moment later is just the surface that's tangent to all of those tiny individual ripples. It's the envelope, the smooth curve that just barely touches the front of each little wavelet. If that sounds abstract, think about it this way. Imagine you're standing at the edge of a still pond, and instead of tossing in one stone, you toss in a whole line of pebbles simultaneously, all in a row. Each pebble creates its own circular ripple, but because they're all in a line and they all hit at the same time, the ripples overlap and reinforce each other along the front edge, and what you see moving outward is a single, smooth, straight wave. Each pebble contributed, but the overall effect is one coherent wave front. That's Huygens' principle in action. And the beauty of it is that it explains so many behaviors of waves that would otherwise seem mysterious. Take diffraction, for instance. You've experienced diffraction your whole life, even if you didn't know the word for it. Have you ever noticed that you can hear someone talking around a corner, even though there's a wall between you? Sound bends around obstacles. It wraps around edges. Light does this too, but because light has such a tiny wavelength compared to everyday objects, the effect is much harder to notice. Sound, with its longer wavelengths, anywhere from about 17 millimeters for the highest frequencies we can hear, up to 17 meters for the lowest, bends around things all the time. A doorway, a building corner, a tree. The sound wave hits the edge, and according to Huygens' principle, the points along the wave front that make it past the edge each become new sources. They radiate outward, filling in the shadow zone behind the obstacle. That's why you can hear music drifting around the corner of a building on a summer evening, even though you can't see the musicians. The sound literally curves around the corner. And here's what's really clever about this framework. It doesn't just explain diffraction, it explains reflection and refraction too. When a wavefront hits a flat surface, each point on that surface becomes a new source, and if you work out the geometry of all those secondary wavelets bouncing back, you get the law of reflection. Angle of incidence equals angle of reflection, the same rule you learned about mirrors. When a wavefront passes from one medium into another, say, from air into water, the speed changes. And that speed change means the wavelets on one side of the boundary are expanding at a different rate than the ones on the other side, which bends the wavefront. That's refraction. One principle, three major wave behaviors, all unified. Huygens published this in 1690 in a work called Traité de la Lumière, Treatise on Light. And while it was primarily about light, the mathematics and the conceptual framework applied to any wave, including sound. Now, I should tell you that Huygens' wave theory didn't win the day immediately, not even close. Because standing on the other side of the debate was Isaac Newton, and when Isaac Newton disagreed with you in the late 17th century, that carried a lot of weight. Newton favored a particle theory of light. He thought light was made of tiny corpuscles, little particles shooting through space. And because Newton was, well, Newton, his view dominated for over a century. It wasn't until the early 1800s that the wave theory of light was definitively revived, largely through the work of Thomas Young and Augustin Jean Fresnel. But for sound, the situation was different. Nobody seriously doubted that sound was a wave phenomenon. The evidence was too direct, too visceral. You could feel it. You could see its effects on surfaces, on water, on flames. The question with sound was never really whether it was a wave, but rather, what kind of wave, and how exactly it behaved in different situations. And this is where we should talk about something that might seem counterintuitive at first. We've been discussing sound as a pressure wave, a longitudinal wave, where the air molecules push and pull back and forth in the same direction the wave is traveling. That's true for sound in air, and it's true for sound in water and other fluids. But when sound enters a solid, like rock or metal or bone, things get more complicated. Because solids can support not just longitudinal waves, where the material compresses and expands along the direction of travel, but also transverse waves, where the material moves side to side, perpendicular to the direction the wave is moving. Think about shaking a rope. The wave travels along the rope, but each point on the rope moves up and down. That's a transverse wave. Fluids can't really support transverse waves because they don't have the rigidity to transmit that sideways shearing motion. But solids can. And this matters enormously for understanding things like earthquakes, where both types of waves, called P waves and S waves by seismologists, travel through the Earth at different speeds and cause different kinds of damage. The P waves, the longitudinal ones, arrive first because they're faster. The S waves, the transverse ones, arrive second but often cause more destruction because of that side-to-side shaking motion. Same physics as sound, same fundamental principles, just applied to a planet instead of a concert hall. So let's come back to the question of how sound behaves when it encounters things, because this is where the story gets really practical, really fast. Huygens gave us the conceptual framework, but it took generations of physicists, mathematicians, and eventually engineers to work out all the implications. One of the most important phenomena is interference. What happens when two or more sound waves overlap in the same space at the same time? Here's the thing about waves. They obey what's called the superposition principle. When two waves meet, they don't bounce off each other like billiard balls. They pass right through each other, and at every point where they overlap, the total disturbance is just the sum of the individual disturbances. So, if two waves arrive at the same point, both pushing the air pressure up, you get a bigger push, constructive interference, a louder sound. But if one wave is pushing up while the other is pulling down, they cancel each other out. Destructive interference, silence, actual silence from two sounds combining. That's wild when you think about it. Two sounds can add up to no sound. This isn't just a theoretical curiosity. It's the principle behind noise-canceling headphones, which is one of the most satisfying applications of wave physics you'll encounter in everyday life. The headphones have tiny microphones on the outside that pick up ambient noise, the drone of an airplane engine, the rumble of a train. A processor inside the headphones analyzes that incoming sound wave and generates a second sound wave that's the exact inverse. Same frequency, same amplitude, but flipped in phase so the peaks line up with the troughs. When the original noise and the anti-noise combine in your ear canal, they cancel. The result is a dramatic reduction in background noise, and all of it comes down to the superposition principle. Destructive interference, engineered on purpose, in real time, thousands of times per second. The technology has gotten remarkably good. Modern noise-canceling systems can reduce low-frequency ambient noise by 20 to 30 decibels, which is a huge perceptual difference. We'll talk about decibels properly later, but for now, just know that a reduction of 10 decibels sounds roughly like cutting the loudness in half. So 30 decibels of reduction makes a roaring airplane cabin sound like a quiet room. But interference does more than just cancel sound. It also creates patterns, beautiful, complex, sometimes maddening patterns. If you've ever been in a room where the sound seems oddly dead in one spot and boomy in another, you've experienced standing waves, a specific kind of interference pattern that forms when sound reflects off walls and overlaps with itself. At certain frequencies, the reflected waves and the incoming waves line up just right, creating fixed points where the air pressure is always at a maximum. Those are called antinodes, and fixed points where the pressure variation is always zero. Those are nodes. It's the same physics that makes a guitar string vibrate in specific patterns. The string is fixed at both ends, and only certain wavelengths fit neatly between those fixed points. Those are the resonant frequencies, the harmonics. And this, right here, is where the physics of sound connects back to something Pythagoras noticed 2,500 years ago with his monochord, that the pleasing musical intervals correspond to simple ratios of string lengths. He was observing resonance and harmonic structure without having the vocabulary for it. The math was the same. The physics was the same. He just didn't know it yet. And resonance. Now there's a concept that deserves some real attention, because it's one of the most powerful and sometimes most dangerous phenomena in all of engineering. The basic idea is simple. Every object that can vibrate has natural frequencies, frequencies at which it prefers to vibrate, frequencies at which even a tiny input of energy gets amplified because the timing is just right. Push a child on a swing, and if you push at exactly the right moment in each cycle, the swing goes higher and higher with minimal effort. That's resonance. The frequency of your pushes matches the natural frequency of the swing. Now imagine that same principle applied to a bridge, or a building, or an aircraft wing. If some external force, wind, footsteps, engine vibration, happens to match the natural frequency of the structure, the vibrations can build and build, growing far larger than the force that's driving them. The most famous example, the one that shows up in every physics textbook, is the Tacoma Narrows Bridge. It was a suspension bridge in Washington State, opened on July 1st, 1940. From the very beginning, the bridge had a reputation for moving in the wind. It would undulate, the roadway rising and falling in gentle waves, and locals actually nicknamed it Galloping Gertie. Drivers reported a strange, almost seasick sensation crossing it. Engineers were aware of the movement, but they believed the bridge was structurally sound. Then, on November 7th, 1940, just 4 months after it opened, a steady wind of about 40 miles per hour set the bridge into increasingly violent oscillations. The movement shifted from vertical undulation to a twisting, torsional mode, and within an hour, the bridge tore itself apart. The whole center span collapsed into the waters of the Tacoma Narrows below. Remarkably, no human lives were lost, though a dog named Tubby, trapped in an abandoned car on the bridge, didn't survive despite rescue attempts. Now, the popular explanation you'll often hear is that the wind frequency matched the bridge's resonant frequency, and that's a reasonable first approximation. But the real story is more nuanced. The phenomenon that destroyed the Tacoma Narrows Bridge is more accurately described as aeroelastic flutter, a self-exciting oscillation where the interaction between the wind and the bridge's own motion created a feedback loop. The bridge's movement changed the way the wind flowed around it, which in turn amplified the movement, which further changed the airflow, and so on. It's related to resonance, certainly, but it's a more complex dynamic instability. And the reason I'm being careful about this distinction is that it matters for how we think about engineering in general. If you walk away thinking resonance is just about matching frequencies, you miss the deeper lesson. Resonance is one kind of feedback. Aeroelastic flutter is another kind of feedback. And the real danger in engineering, the thing that keeps structural engineers up at night, is any situation where a system's response to a force ends up amplifying that force instead of dampening it. That's the thread that connects a wine glass shattering when a soprano hits the right note to a bridge ripping itself apart in a steady wind. It's not always the same mechanism, but it's always the same underlying idea. Energy going in faster than it can dissipate. And here's why this matters beyond bridges. That same concept, feedback-driven oscillation, shows up everywhere in the world of sound. It's the screech you hear when someone holds a microphone too close to a speaker. The microphone picks up the sound from the speaker, sends it through the amplifier, which sends it back out the speaker louder, which the microphone picks up again, and around it goes, each loop adding energy until you get that piercing howl. Audio engineers call it feedback, plain and simple. And managing it is one of the fundamental challenges of live sound reinforcement. Every concert you've ever been to, there's someone at a mixing board whose job partly involves making sure that loop never gets out of control. They use equalization to notch out the specific frequencies most likely to feed back in that particular room, with that particular arrangement of speakers and microphones. It's a constant, subtle battle against the physics of sound waves bouncing around an enclosed space. But let's pull back from feedback for a moment, because there's something else about the Tacoma Narrows story that's worth sitting with. The bridge was designed by Leon Moisseiff, a highly respected engineer who had worked on the Manhattan Bridge and contributed to the design of the Golden Gate Bridge. He wasn't some amateur. He was one of the leading bridge designers in America. And his design for the Tacoma Narrows Bridge was, by the standards of the time, elegant. It used a very slender, shallow plate girder for the deck instead of the deep, heavy trusses that were common in older suspension bridges. It was lighter, cheaper, more graceful looking, and it was exactly that slenderness, that elegance, that made it vulnerable to the wind. The lesson the engineering community took from the disaster was profound. It fundamentally changed how suspension bridges were designed. After Tacoma Narrows, wind tunnel testing became standard practice. Engineers started thinking seriously about aerodynamic stability, not just static load-bearing capacity. The replacement bridge, completed in 1950, was much stiffer and included open trusses that let wind pass through rather than pushing against a solid surface. Every major suspension bridge built since then carries the ghost of Galloping Gertie in its design DNA. So resonance and its cousins, flutter, feedback, coupled oscillations, these are the dramatic side of how sound and vibration interact with the physical world. But there's a quieter, more everyday side to all this that's just as important, and it has to do with something we haven't really talked about yet: how sound behaves when it hits a boundary, when it meets a wall, a floor, a ceiling, the surface of a lake, the edge of a forest. What happens at that interface between one medium and another? You already know intuitively that sound bounces off things. That's what an echo is. You shout toward a cliff face, and a moment later your voice comes back to you. The ancient Greeks knew about echoes. They even had a myth about it, the nymph Echo, cursed to repeat only the last words spoken to her. But understanding the physics of reflection took a lot longer. The basic rule is beautifully simple. The angle of incidence equals the angle of reflection. Sound hits a flat surface, and it bounces off at the same angle it arrived, just mirrored. It's the same law that governs light bouncing off a mirror, and that's not a coincidence. It's a fundamental property of wave behavior. Now that's the idealized version. In reality, most surfaces aren't perfectly flat and rigid. They have texture, they have give, they absorb some of the sound energy and scatter the rest in various directions. And this is where things get really interesting from an engineering perspective, because the way a room handles sound reflections is basically what determines whether that room sounds good or terrible. Think about a bathroom. Hard tile walls, hard floor, hard ceiling, all close together. You sing in the shower, and your voice sounds amazing. Rich, full, reverberant. That's because the sound waves are bouncing off all those hard surfaces with very little absorption, and they're reaching your ears from many different directions with very short delays. The reflections pile up on top of each other, filling in the gaps, smoothing out the imperfections in your voice. It's flattering. It's also, from an acoustic engineering standpoint, a highly reverberant space. Now think about the opposite. Imagine standing in the middle of a huge open field, no buildings around, no trees, just flat ground and open sky. You clap your hands and the sound just goes. It radiates outward and never comes back. There's no echo, no reverb, almost no sense of space at all. Acousticians call this a free field condition. Sound propagating without any reflections. It sounds dry, immediate, almost uncomfortably naked. Your voice in that field would sound thin and exposed compared to the bathroom version. Every real room falls somewhere on the spectrum between those two extremes. And the art and science of architectural acoustics is fundamentally about controlling where on that spectrum a particular space lands. And the person who arguably invented this field, who turned it from guesswork into science, was a physicist named Wallace Clement Sabine. Here's the thing about Sabine. He didn't set out to revolutionize acoustics. He was a young physics professor at Harvard in the 1890s, and he got handed a problem that nobody else wanted. Harvard had just opened a new lecture hall in the Fogg Art Museum, and it was acoustically disastrous. Speakers were unintelligible. Words blurred into each other, swallowed by a wash of echoes and reverberations. The university president asked Sabine to fix it, apparently because Sabine was junior enough that he couldn't say no. So Sabine did something remarkably methodical. He started measuring. He would work late at night, when the building was empty and quiet, using organ pipes as sound sources and a stopwatch to time how long it took for sound to decay to inaudibility. He dragged seat cushions from a nearby theater into the lecture hall, adding them in batches, and measured the reverberation time after each edition. Cushion by cushion, he mapped the relationship between the amount of absorptive material in a room and how long sound lingered. What he discovered was a formula, now called the Sabine equation, that relates reverberation time to the volume of a room and the total absorption of its surfaces. The bigger the room, the longer the reverberation. The more absorptive material you add, the shorter it gets. It sounds obvious when you say it like that, but Sabine was the first person to quantify it precisely, to give architects and engineers actual numbers they could use to predict how a room would sound before it was built. His formula is still used today. Every concert hall, every recording studio, every lecture theater, every movie cinema. The acoustic design starts with Sabine's equation, and the unit of sound absorption is actually named after him. One Sabin is the absorption equivalent of 1 square foot of a perfectly absorptive surface, a surface that swallows every bit of sound that hits it and reflects nothing back. Different materials have different absorption coefficients. A thick carpet might absorb 70 or 80% of the sound energy that hits it at mid-frequencies. A sheet of glass might absorb only about 3 or 4%. A heavy velvet curtain may be 50 to 60%. And these numbers change depending on the frequency of the sound, which is a crucial detail. Most soft, porous materials are much better at absorbing high frequencies than low frequencies. That's why a room with lots of carpet and curtains can still have a boomy, muddy quality. The low-frequency sound waves, with their long wavelengths, aren't being absorbed effectively. They're bouncing around, building up, muddying everything. This frequency-dependent absorption is one of the great challenges of acoustic design. If you're designing a concert hall, you don't just want the right overall reverberation time. You want the right reverberation time across the entire frequency spectrum. Too much high-frequency absorption, and the room sounds dull, muffled, lifeless. Too little low-frequency absorption, and it sounds boomy and unclear. The ideal is a balanced decay, where all frequencies fade at roughly the same rate. And achieving that balance requires a careful combination of different materials and structures. Thick, porous absorbers for the highs. Tuned panel absorbers, or Helmholtz resonators for the lows. Diffusers to scatter the mid-range reflections evenly throughout the space. Helmholtz resonators, by the way, those are named after Hermann von Helmholtz, the 19th century German physicist who was arguably the most important figure in the science of sound during his era. Helmholtz was a polymath in the truest sense. He made foundational contributions to thermodynamics, optics, electrodynamics, and the physiology of perception. But his 1863 book, On the Sensations of Tone, is one of the landmark works in the history of acoustics. In it, Helmholtz laid out a comprehensive theory of how we perceive musical sound, how the ear analyzes complex tones into their component frequencies, how timbre works, why different instruments playing the same note sound different. And those resonators he invented were beautifully simple devices. Imagine a hollow brass sphere with a small opening on one side and a narrow tube on the opposite side that you'd put near your ear. Each sphere was tuned to resonate at a specific frequency. When you held it up in a room full of sound, it would amplify just that one frequency, letting you isolate individual harmonics from a complex sound. It was like having a filter for your ear. Helmholtz used sets of these resonators to painstakingly analyze the harmonic content of vowel sounds, musical instruments, and tuning forks. He showed that what we perceive as the color or quality of a sound, the thing that makes a trumpet sound different from a clarinet, even when they're playing the same note at the same volume, is determined by the relative strengths of the harmonics present in the sound. The fundamental frequency tells you the pitch. The harmonics tell you everything else. This was a huge insight. It connected the physics of vibration directly to the psychology of perception, and it built on something that a French mathematician had figured out decades earlier. Something so powerful, so far-reaching in its implications, that it touches almost every corner of modern technology. I'm talking about Joseph Fourier and his radical idea that any complex waveform, no matter how complicated, can be broken down into a sum of simple sine waves. Each sine wave has its own frequency, its own amplitude, its own phase. Add them all together, and you reconstruct the original complex wave perfectly. It's called Fourier analysis. And when Fourier first proposed the basic idea in 1807, in the context of heat conduction rather than sound, several prominent mathematicians were skeptical. Lagrange in particular thought the claim was too broad, too sweeping. But Fourier was right, and the mathematical framework he developed turned out to be one of the most versatile tools in all of science and engineering. Think about what this means for sound. When you hear a symphony orchestra playing a chord, the air pressure at your eardrum is doing something incredibly complicated. It's the sum of hundreds of different vibrations from dozens of different instruments, all overlapping, all interfering with each other. And yet, Fourier's mathematics tells us that this impossibly complex pressure wave can be decomposed into individual sine waves, each one corresponding to a single frequency. Your ear, remarkably, does something very much like this decomposition in real time. The cochlea, that snail-shaped structure in your inner ear, is essentially a biological Fourier analyzer. Different positions along its length respond to different frequencies. High frequencies near the base, low frequencies near the apex. It's performing a spectral analysis of every sound you hear, thousands of times per second, without you ever thinking about it. And here's where Fourier's idea leaps from pure science into the engineering that shapes your daily life. Because once you can break a complex signal into its frequency components, you can manipulate those components individually. You can filter out noise. You can compress audio files by throwing away the frequencies that human ears can barely hear. That's essentially what MP3 compression does, and it's built on a computational version of Fourier analysis called the Fast Fourier Transform, or FFT. The FFT algorithm, published by James Cooley and John Tukey in 1965, made it practical to do Fourier analysis on digital computers quickly enough to be useful in real time. It's been called one of the most important algorithms of the 20th century, and that's not hyperbole. It's inside your phone right now. It's in every digital audio system, every piece of voice recognition software, every medical imaging device that uses ultrasound. It's in the software that processes seismic data to find oil deposits, and in the systems that clean up audio recordings for forensic analysis. But I'm getting ahead of myself, because to really understand how we got from Fourier's mathematics to the digital audio world we live in now, we need to talk about something that happened in between, something that changed the relationship between humans and sound more fundamentally than anything since the invention of musical instruments. We need to talk about the moment someone figured out how to capture sound, to freeze it in time, to make it permanent. And that story starts in a place you might not expect, not with Thomas Edison, though he'll show up soon enough, but with a French printer and bookseller named Edouard Léon Scott de Martinville, who in 1857 built a device he called the phonautograph. And what's fascinating about Scott's invention is that it was never meant to play anything back. That's the part that catches everyone off guard. Scott de Martinville didn't invent a way to listen to recorded sound. He invented a way to see it. His phonautograph was designed to trace the shape of sound waves onto a sheet of paper blackened with soot from an oil lamp. The idea was that you'd speak or sing into a barrel-shaped horn, and at the narrow end of that horn was a flexible membrane, a thin piece of parchment or pig bladder, that would vibrate in response to the sound. Attached to that membrane was a tiny stylus, a stiff bristle, and as the membrane vibrated, the bristle would scratch a delicate, wavy line through the soot on a rotating cylinder. And that was it. That was the whole device. You'd end up with a visual trace of the sound wave, a squiggly line etched in lamp black, and Scott thought This was going to be revolutionary, not because you could hear it again, but because you could study it. He imagined a kind of shorthand, a way to transcribe speech directly from sound into visible patterns. He thought maybe people could learn to read these traces the way you'd read text on a page. And here's what's poignant about Scott's story. He was a printer and bookseller by trade, a man deeply interested in language and writing, and he saw the phonautograph as a writing instrument. The word itself, phonautograph, means self-writing of sound. He was obsessed with the idea that sound could write itself down, that the air could be its own stenographer. He patented the device in 1857, a full 20 years before Edison's phonograph, and he spent years refining it, producing dozens of these soot-covered recordings, these phonautograms, which he carefully labeled and stored. But he never figured out how to play them back. He never even tried, really, because that wasn't the point for him. The point was the visual record. Now, here's where the story gets a little bittersweet. For over a century, Scott's phonautograms sat in archives, these fragile sheets of paper with their faint wavy lines, and nobody could hear what was on them. They were silent artifacts of sound. Then, in 2008, a group of researchers at the Lawrence Berkeley National Laboratory in California used high-resolution optical scanning and digital signal processing, the descendants of that very Fourier analysis we were just talking about, to convert those visual traces back into audio. They essentially read the squiggly lines, calculated what frequencies and amplitudes they represented, and synthesized the corresponding sound waves digitally. And what they recovered was a 10-second recording of someone singing Au clair de la lune, a French folk song, scratched into soot on April 9th, 1860. It's scratchy, it's ghostly, it's barely recognizable, but it's a human voice from 1860, 17 years before Edison. It's the oldest known recording of a recognizable human voice, and the man who made it never heard it played back. He died in 1879, the same year Edison was touring the world demonstrating his phonograph, and as far as we know, Scott was bitter about it. He felt Edison had stolen his idea, or at least gotten credit for something he'd pioneered. And in a way, he was right. But in another way, he'd missed the crucial leap. Because Edison's insight, when he built the phonograph in 1877, wasn't just that you could record sound. It was that you could record it and play it back. That distinction between capturing and reproducing is the whole game. Scott could write sound down, but Edison could make it speak again. And the mechanism Edison used was, in principle, beautifully simple. Instead of scratching a line through soot on a flat surface, Edison's phonograph used a stylus to cut a groove into a sheet of tinfoil wrapped around a rotating cylinder. You'd speak into a horn. The diaphragm at the narrow end would vibrate. The stylus would press into the foil with varying depth depending on the pressure wave. And you'd end up with a physical groove whose shape was an analog of the original sound wave. Then, and this is the key, you'd put the stylus back at the beginning, turn the cylinder again, and the groove would push the stylus, which would vibrate the diaphragm, which would push air, which would recreate the sound. The same mechanism in reverse. Record and playback using the same physical principle, just running the chain of cause and effect in the opposite direction. Edison reportedly shouted, "Mary had a little lamb," into the device during the first test, and when it played back his own voice, even he was startled. He later said he was always afraid of things that worked the first time. The tinfoil phonograph was crude. The recordings degraded after just a few playbacks because the foil was so fragile. But the demonstration was electrifying. Edison became world famous almost overnight. He was invited to the White House to demonstrate it for President Hayes. People called it the talking machine, and some genuinely didn't believe it was real. There were accusations that Edison was a ventriloquist, that there was someone hidden inside the device. But here's the thing about Edison. He was a brilliant inventor, but sometimes a terrible predictor of his own invention's futures. He initially thought the phonograph would be most useful as a business dictation machine, a way for executives to record letters that secretaries could type up later. He didn't immediately see music as the killer application. That took years, and it took competition. Because while Edison was focused on cylinders, other inventors were exploring different approaches. Alexander Graham Bell, yes, the telephone bell, along with his cousin Chichester Bell and Charles Sumner Tainter, developed the graphophone in the mid-1880s, which replaced tinfoil with wax-coated cardboard cylinders. The wax was more durable, the grooves were cleaner, and the recordings lasted longer. Edison, competitive to his core, responded by switching to solid wax cylinders for his own improved phonograph. But the real disruption came from Emil Berliner, a German immigrant living in Washington, D.C., who in 1887 patented the gramophone. And Berliner's key innovation was geometric. Instead of recording sound as a groove spiraling around a cylinder, he recorded it as a groove spiraling on a flat disc. Think about what that means practically. Cylinders are awkward to manufacture, awkward to store, and you can't easily stamp out copies. But a flat disc? You can press a flat disc the same way you print a page. You make a master, you create a mold, and you stamp out as many copies as you want. Berliner's disc format made mass production of recorded music economically viable for the first time. It took about a decade for the technology to mature, for the sound quality to improve enough to compete with cylinders. But by the early 1900s, the disc was winning. And that format, a flat disc with a spiral groove, would dominate recorded music for nearly a century, through shellac 78s, through vinyl LPs, all the way into the 1980s when digital compact discs finally took over. Now let's slow down and think about what's actually happening in that groove, because it's a gorgeous piece of analog engineering. When you look at a vinyl record under a microscope, the groove isn't smooth. It's a continuous undulating wave carved into the surface. The shape of that wave is a physical analog of the original sound wave's pressure variations. When the record spins and the stylus, the needle, rides in the groove, the walls of the groove push the stylus side to side. Those tiny lateral movements are transmitted up through the tone arm to a cartridge, which contains either a tiny magnet surrounded by coils of wire or a piezoelectric crystal. Either way, the mechanical vibration of the stylus gets converted into an electrical signal, and that electrical signal is an analog of the original sound wave. Amplify it, send it to a speaker, and the speaker cone pushes air in the same pattern, and you hear music. Think about the chain of transformations there. A singer's vocal cords vibrate, pushing air molecules into pressure waves. Those pressure waves hit a microphone diaphragm, which vibrates and generates an electrical signal. That electrical signal drives a cutting lathe that carves a groove in a master disc. The groove is a physical record of the vibration pattern. Decades later, a needle rides that groove, vibrates, generates a new electrical signal, drives a speaker, and pushes air into pressure waves that hit your eardrum, which vibrates, sending signals to your brain. It's the same pattern, the same wave shape, passed from medium to medium to medium, air to membrane to electricity, to groove to needle to electricity, to speaker cone to air to eardrum. Each step is a transducer, a device that converts energy from one form to another while preserving the essential pattern. And that concept, transduction, is one of the most important ideas in all of sound engineering. Every link in the audio chain is a transducer. Your ear is a transducer. A microphone is a transducer. A speaker is a transducer. And the quality of your audio experience depends on how faithfully each transducer preserves the original wave pattern. Any distortion introduced at any step in the chain, a scratched record, a cheap speaker, a poorly designed microphone, degrades the signal. This is why audiophiles obsess over every component in their playback systems, because each one is a potential point of failure, a place where the pattern can be corrupted. But let's come back to the history, because the story of recorded sound in the early 20th century isn't just about formats and mechanisms. It's about what recorded sound did to human culture. Before the phonograph and the gramophone, if you wanted to hear music, someone had to be playing it right there, in the same room. Music was an event, a live performance, something that existed only in the moment. You could write it down as notation on a page, sure, but that was a set of instructions, not the sound itself. The phonograph changed that relationship in a way that's hard to overstate. Suddenly, a performance could be captured, duplicated, shipped across oceans, and played back years later. A singer could be dead, and their voice could still fill a room. That's a profound thing. It severed the ancient link between the production of sound and the experience of hearing it. Sound became something you could own, something you could hold in your hand, something you could collect on a shelf. And this transformation didn't just change how people consumed music, it changed how music was made. Before recording, musicians played for live audiences, and the acoustic properties of the performance space were part of the experience. Concert halls were designed with reverberation in mind, the way Sabine had figured out. But recording studios? That was a different problem entirely. Early acoustic recording, before electrical microphones, required performers to crowd around a large horn and play as loudly as possible, because the only energy driving the cutting stylus was the acoustic energy of the sound itself. Orchestras had to be rearranged, with louder instruments farther back and quieter ones crammed near the horn. Singers had to project directly into the bell. The frequency response was terrible. Bass was almost non-existent. High frequencies were muffled. If you've ever heard a recording from the acoustic era, from before about 1925, you know that tinny, distant quality, like the music is coming from the bottom of a well. Everything changed with the introduction of electrical recording in the mid-1920s, and the person at the center of that revolution was an engineer at Western Electric named Joseph Maxfield. And Maxfield is one of those figures who doesn't get nearly enough credit for how much he changed the world. He wasn't a musician, wasn't a composer, wasn't a performer. He was a telephone engineer. And that background turns out to be exactly what was needed, because the problem of recording sound electrically was at its core a telephone problem. You're taking acoustic energy, sound waves hitting a diaphragm, and converting it into an electrical signal. That's literally what a telephone does. Alexander Graham Bell had figured out the basic principle back in the 1870s, and by the 1920s, the engineers at Bell Labs and Western Electric had gotten very, very good at building microphones, amplifiers, and loudspeakers. They understood electrical signal chains in a way that nobody in the recording industry did. So Maxfield and his colleague Henry Harrison set about applying everything they knew about telephone engineering to the problem of sound recording. And the key insight was this: instead of relying on raw acoustic energy to physically drive a cutting stylus, you could use a microphone to convert sound into an electrical signal. amplify that signal with vacuum tube amplifiers, and then use the amplified electrical signal to drive the stylus. Think about what that means. In the old acoustic system, the only power you had was whatever sound energy the performers could push into that horn. That's not a lot of energy. Sound waves carry remarkably little power. We talked about that earlier, how the threshold of hearing is just 10 to the minus 12 watts per square meter. Even a full orchestra playing fortissimo is only producing a few watts of acoustic power total. But with electrical amplification, you could take that tiny signal from the microphone and boost it enormously. The stylus could now cut deeper, more precise grooves. You could capture frequencies that the old mechanical system simply couldn't handle. Maxfield and Harrison's system, which they called the orthophonic process, was licensed to the Victor Talking Machine Company, and the first electrically recorded discs hit the market around 1925. The difference was staggering. Suddenly, recordings had bass. They had presence. The frequency range jumped from maybe 250 to 2,500 hertz in the acoustic era to something like 50 to 6,000 hertz with electrical recording. That might not sound like much compared to the full range of human hearing. Remember, we can hear from about 20 hertz up to 20,000, but it was a massive leap. For the first time, you could hear something on a record that actually sounded like it resembled the original performance. The bottom end of a cello, the sizzle of a cymbal, the natural warmth of a human voice, all of that started coming through. And here's what's really fascinating about this transition. It didn't just improve sound quality, it fundamentally changed the art of recording. In the acoustic era, performers had to physically arrange themselves around the horn based on volume. A vocalist would stand inches from the bell. A violin might be right behind them, and the bass player would be way in the back because the bass frequencies weren't going to be captured anyway. With a microphone, none of that mattered anymore. You could place the microphone wherever you wanted. You could have multiple microphones in different positions. Performers could stand at natural distances from each other and play the way they would in a concert hall. Singers didn't have to belt into a horn. They could sing softly, intimately, and the microphone would pick it up. This is actually where the whole concept of the crooner comes from. Bing Crosby, one of the biggest stars of the 20th century, built his entire career on a vocal style that would have been literally impossible to record before electrical microphones. He sang quietly, smoothly, conversationally. In the acoustic era, that kind of singing would have produced grooves so shallow they'd be inaudible on playback. But with a sensitive condenser microphone and a good amplifier chain, Crosby's gentle baritone could be captured in all its warmth and then amplified to fill a living room. The microphone didn't just record the voice, it created a new kind of voice, a new kind of intimacy between performer and listener. And that idea, that the recording technology shapes the art, not just the other way around, is one of the most important threads running through the entire history of sound. Every time the technology changes, the music changes with it. Every single time. But let's stay with the engineering for a moment, because the electrical recording chain introduced a concept that would become absolutely central to everything that followed: the idea of the signal path. Once sound becomes an electrical signal, you can do things to it. You can amplify it, obviously, but you can also filter it. You can boost certain frequencies and cut others. You can mix multiple signals together. You can send a signal through a wire to a completely different location. Each of these operations is a link in a chain, and the quality of your final recording depends on the quality of every single link. A noisy amplifier introduces hiss. A poor microphone misses certain frequencies. A bad connection adds crackle. Engineers started thinking very carefully about signal-to-noise ratio, the relationship between the sound you want and the unwanted noise that creeps in at every stage. And this is still, to this day, one of the most fundamental concepts in audio engineering. Every piece of equipment in the chain either preserves the signal faithfully or degrades it slightly. And the art of recording is, in many ways, the art of minimizing that degradation across dozens of components. Now, the other half of this electrical revolution was playback. It wasn't enough to record electrically. You also needed to play back electrically. The old acoustic phonograph used a horn as a mechanical amplifier, with the needle's vibrations directly driving a diaphragm at the narrow end of the horn. Victor's new orthophonic Victrola, designed by Maxfield, used a carefully engineered folded horn that dramatically improved the mechanical playback quality. But the real leap came with electrical playback. A pickup cartridge that converted the needle's vibrations into an electrical signal, an amplifier to boost it, and a loudspeaker to convert it back into sound waves. And the loudspeaker itself is a beautiful piece of engineering. The most common type, the moving coil dynamic speaker, works on exactly the same principle as a microphone, but in reverse. You have a coil of wire attached to a cone, a diaphragm, and that coil sits inside the field of a permanent magnet. When electrical current flows through the coil, the interaction between the coil's electromagnetic field and the permanent magnet's field pushes the coil back and forth, and the cone moves with it, pushing air, creating sound waves. It's the motor principle, the same physics that makes electric motors spin, just applied in a linear, back and forth motion instead of a rotary one. The varying electrical signal from the amplifier makes the coil move in a pattern that mirrors the original sound wave, and the cone reproduces that pattern as pressure variations in the air. Think about the full chain now. A singer's vocal cords vibrate, creating pressure waves in the air. Those waves hit a microphone diaphragm, which vibrates. A coil attached to that diaphragm moves through a magnetic field, generating a tiny electrical current that mirrors the original wave. That current is amplified, and the amplified signal drives a cutting stylus that carves a groove in a spinning disc. Later, a needle traces that groove, vibrating a pickup that generates a new electrical signal. That signal is amplified and sent to a loudspeaker, where a coil in a magnetic field pushes a cone back and forth, creating pressure waves in the air that enter your ear canal, vibrate your eardrum, move the ossicles, create waves in the cochlear fluid, bend the hair cells on the basilar membrane, and trigger nerve impulses that your brain interprets as a voice. Every single step in that chain is a transduction, energy-changing form, from mechanical to acoustic to electrical to mechanical to acoustic again. And the miracle is that after all those transformations, what comes out still sounds like a human voice. Not perfectly, not yet, not in the 1920s, but recognizably, emotionally, unmistakably human. The next few decades brought refinement after refinement. Magnetic tape recording arrived in the 1930s and 1940s, largely developed in Germany by engineers at AEG and the chemical company IG Farben, who created a plastic tape coated with iron oxide particles. The principle is elegant. You magnetize tiny particles on a moving tape in a pattern that corresponds to the audio signal. A recording head is essentially an electromagnet with a tiny gap. The tape passes over that gap, and the varying magnetic field from the audio signal magnetizes the particles in a corresponding pattern. On playback, the magnetized tape passes over a similar head, and the varying magnetic field from the tape induces a tiny electrical current in the head's coil. Same principle, reversed. American soldiers discovered this technology in German radio stations at the end of World War II, and one of the people most responsible for bringing it to America was Bing Crosby. Yes, the same Bing Crosby. He hated doing live radio broadcasts because they required him to perform the same show twice, once for the East Coast and once for the West Coast. When he heard about magnetic tape, he immediately saw the potential. Record once, broadcast whenever you want. He invested heavily in the Ampex Corporation, which became the dominant American tape recorder manufacturer, and by the late 1940s, magnetic tape had revolutionized both the recording and broadcast industries. And tape introduced something that grooves on a disc never really could: editing. With a disc, the recording was a single continuous cut. If someone made a mistake 3 minutes in, you started over. But tape you could cut with a razor blade and splice together with adhesive tape. You could take the best parts of multiple performances and assemble them into a single perfect take. You could rearrange sections, remove mistakes, even, with enough skill, edit out individual notes. This was a seismic shift. For the first time, a recording didn't have to represent a single continuous performance. It could be constructed, assembled, sculpted. The recording became a creative work in its own right, separate from any single live performance. And this idea would reach its full flowering in the 1960s, when a producer working in a small studio in London started treating the recording studio itself as a musical instrument, layering sounds on top of sounds, bouncing tracks between tape machines, creating sonic textures that could never exist in a live performance. That producer's name was George Martin, and the band he was working with was the Beatles. And what George Martin and the Beatles did together in the mid-1960s is one of the most extraordinary stories in the history of recorded sound. Not because it was the most technically sophisticated work ever done, it wasn't, but because it changed what everyone thought a recording could be. Think about where we started. Edison's phonograph was a device for capturing a moment. You sang into a horn, a needle scratched a groove, and what you got back was a copy of that moment, imperfect but recognizable. Even with all the improvements we've talked about, electrical recording, microphones, amplifiers, better media, the basic idea hadn't really changed. A recording was still fundamentally a document of a performance. A very good document, sure. A document with wider frequency response and better signal-to-noise ratio. But still a document. What George Martin and the Beatles did was abandon that idea entirely. They started making recordings that were the thing itself, not a copy of something that happened, but something that only existed as a recording. Now Martin was classically trained, a musician himself, and he'd been working at EMI's Abbey Road studios for years before the Beatles came along. He'd produced comedy records, orchestral sessions, all kinds of things. He understood the equipment intimately. And the Beatles, especially John Lennon and Paul McCartney, were endlessly curious, always asking, "What happens if we do this?" And Martin's answer was usually, "Let's find out." So they started experimenting. They'd record a vocal track and then play it back at half speed while recording a piano on top of it. So when you played the combined result at normal speed, the piano sounded an octave higher and twice as fast, with this strange, bright, harpsichord-like quality. That's how they got the keyboard sound on In My Life from 1965. Martin played the solo at half tempo on a piano. They sped the tape up, and it became something that sounds like no instrument that actually exists. They'd feed guitar signals through a rotating Leslie speaker, which was designed for organs. It has a spinning horn inside that creates this swirling, Doppler-shifted sound. They'd run vocals through guitar amplifiers, deliberately overloading the signal to create distortion. They'd take a recording, cut the tape into pieces, throw them in the air, and splice them back together in random order. That's literally how parts of Being for the Benefit of Mr. Kite were assembled. And here's what's really important about all of this from an engineering perspective. They were working with 4-track tape machines. 4 tracks. That's it. If you wanted more layers than 4, you had to bounce, meaning you'd mix multiple tracks down onto one track of a second machine, freeing up tracks on the first machine, then add more layers, then bounce again. Every bounce added noise. Every generation of copying degraded the signal. So there was this constant tension between creative ambition and the physical limitations of the medium. And this is where the signal-to-noise ratio we talked about earlier becomes so tangible. Each bounce was like making a photocopy of a photocopy. The music got a little hazier, a little hissier each time. The engineers at Abbey Road, people like Norman Smith and Ken Townsend, were performing absolute miracles of signal management, trying to keep the noise floor as low as possible while stacking layer upon layer of sound. The fact that Sgt. Pepper's Lonely Hearts Club Band, released in 1967, sounds as good as it does is a testament to extraordinary engineering skill, not just musical genius. That album was constructed over about 700 hours of studio time, which was unheard of at the time. Most pop albums were knocked out in a few days. And the result was something that couldn't be performed live. It existed only as a recording. The studio had become the instrument, just as we said. But let's step back from the Beatles for a moment, because something else was happening in the 1960s that would ultimately matter even more for the future of sound. And it starts with a question that engineers had been thinking about for decades. What if, instead of recording sound as a continuous physical trace, a groove in wax, a pattern of magnetic particles on tape, you could record it as numbers? This idea goes all the way back to a paper published in 1928 by a Swedish-American engineer named Harry Nyquist, working at Bell Labs. Nyquist was thinking about telegraph systems, about how much information you could send through a communication channel, and he established something fundamental. If you want to accurately capture a signal that contains frequencies up to some maximum frequency, you need to sample that signal at least twice per cycle of that maximum frequency. So if you're trying to capture audio up to 20,000 hertz, roughly the upper limit of human hearing, you need to take at least 40,000 samples every second. This became known as the Nyquist theorem, and it was later refined and rigorously proven by Claude Shannon, also at Bell Labs, in his landmark 1949 paper on information theory. Shannon showed that if you sample at or above the Nyquist rate, you can perfectly reconstruct the original continuous signal from those discrete samples. Not approximately, perfectly. Every detail of the original wave is captured in those numbers as long as you've sampled fast enough. Now think about what that means. It means that a continuous, flowing, infinitely detailed sound wave can be represented exactly, with zero loss, by a list of numbers. That's a profound idea. It means that the analog world and the digital world aren't fundamentally different in what they can express. They're just different languages for saying the same thing. And once your sound is a list of numbers, everything changes. You can copy it without any degradation. Remember the bounce problem with tape? Every copy added noise, but a number is a number. You can copy the number 42 a million times, and it's still 42. There's no generation loss. You can also manipulate those numbers with mathematics, filter them, combine them, transform them, with a precision that's simply impossible in the analog domain. The challenge, of course, was building hardware that could actually do this fast enough. Taking 40,000 samples per second, converting each one to a number, storing all those numbers. In the 1950s and 1960s, this required rooms full of equipment and was absurdly expensive. But the technology kept advancing. Transistors replaced vacuum tubes. Integrated circuits replaced individual transistors. And by the 1970s, digital audio was starting to become practical. The first major digital recording systems were developed independently in several places. In Japan, Nippon Columbia, known as Denon, made some of the earliest digital recordings in 1971 and 1972, using custom-built converters and modified video recorders to store the data. The audio quality was remarkable. No tape hiss, no wow and flutter, that slight wavering in pitch caused by imperfect tape transport speed. Just the music, captured as numbers and played back with a clarity that stunned engineers who heard it. But the real revolution came with a consumer format. And this is where we get to the compact disc, which is one of those inventions that seems simple in retrospect, but required solving an enormous number of engineering problems simultaneously. The CD was developed jointly by Philips, the Dutch electronics company, and Sony, the Japanese giant, in the late 1970s. Philips had been working on optical disc technology using a laser to read information from a spinning disc, and Sony had deep expertise in digital audio signal processing. They came together, and by 1982, the compact disc was on the market. Here's how it works, and it's worth understanding because it's a beautiful piece of engineering. The disc itself is a polycarbonate plastic disc about 12 centimeters across, with a thin layer of aluminum inside. On that aluminum layer, there's a spiral track, somewhat like a vinyl records groove, but instead of wavy walls, it has a sequence of tiny pits and flat areas called lands. The pits are astonishingly small, about half a micrometer wide. That's half a millionth of a meter. A laser beam, focused to a tiny spot, shines on the track as the disc spins. When the laser hits a flat land, the light reflects cleanly back to a photodetector. When it hits the edge of a pit, the light scatters and the reflected intensity drops. So the photodetector sees a pattern of bright and dim, ones and zeros, essentially. Those ones and zeros encode the audio samples. The standard sampling rate chosen for the CD was 44,100 samples per second, comfortably above the Nyquist rate for 20,000 Hz audio. Each sample is stored with 16-bit resolution, meaning each sample is represented by a number that can have any of about 65,500 possible values. That gives you a theoretical dynamic range of about 96 decibels, the difference between the quietest and loudest sounds the format can capture. Compare that to vinyl, which might give you 60 or 70 decibels on a good day, or tape, which was in a similar range. The CD was a massive leap in fidelity. But here's the thing that doesn't get talked about enough. The raw data on a CD would be useless without an extraordinary amount of error correction. Think about it. A tiny scratch, a speck of dust, a microscopic flaw in the manufacturing process, and suddenly, some of your ones and zeros are wrong. And wrong numbers mean wrong audio samples, which means clicks, pops, or silence. So the engineers at Philips and Sony developed a sophisticated error correction system called CIRC, Cross-Interleaved Reed-Solomon Coding. What it does, in essence, is spread the data out and add redundant information so that even if a chunk of data is lost or corrupted, the system can reconstruct what was supposed to be there. It's like writing every sentence of a book twice in two different places, so that if coffee spills on one page, you can recover the text from the other copy. The actual implementation is much more elegant than that, using mathematical coding theory that goes back to work by Irving Reed and Gustav Solomon in 1960. But the principle is the same. Redundancy enables recovery, and this error correction is astonishingly effective. A CD can have a scratch several millimeters long and still play perfectly, because the data that was under that scratch has been distributed across the disk and can be reconstructed from the redundant copies. You've probably experienced this yourself, a slightly scratched CD that plays just fine. That's CIRC doing its job. It's only when the damage overwhelms the error correction's capacity that you hear glitches. Now, the compact disc was a commercial phenomenon. It essentially killed the vinyl record as a mainstream format within a decade, though vinyl would later stage a remarkable comeback, which is a story for another time. But the CD was also, in a way, the beginning of a much larger transformation. Because once music was digital, once it was just numbers, it could be stored on any medium that stores numbers. It didn't have to be a special disk with a laser. It could be a hard drive, a flash memory chip, a signal transmitted over a network. And that realization is what led eventually to the world we live in now, where most of the music people listen to has never existed as a physical object at all. It's just data, flowing through fiber optic cables and wireless signals, decoded by the processors in your phone or your laptop or your smart speaker. And this brings us to something we touched on earlier, MP3 compression and the psychoacoustic principles behind it. But there's a deeper story here about how digital audio processing opened up possibilities that the analog world simply couldn't match. Because once your sound is numbers, you can do things to it that would have seemed like magic to George Martin bouncing tracks between 4-track tape machines in 1966. You can have not 4 tracks, but 400, each one perfectly clean, each one independently adjustable. You can undo any change. You can try something wild, and if it doesn't work, just restore the previous version. The entire creative process changes when the medium has essentially infinite flexibility and zero degradation. And the person who might have appreciated this most, who spent his career pushing against the physical limits of analog recording, was someone working in a very different musical world from the Beatles, someone whose obsessive perfectionism and visionary approach to multi-track recording helped create the template for modern music production. His name was Les Paul. And yes, he's the same Les Paul whose name is on one of the most famous electric guitar designs in history, but his contributions to recording technology were arguably even more important than his contributions to guitar design. And what Les Paul figured out in the 1940s and 1950s, working in his home studio with custom-modified tape machines, was that recording didn't have to be a single performance captured in a single moment. It could be built, layer by layer, one voice at a time, one instrument at a time, until you had something that no group of musicians could ever play live. Because it was one person, multiplied. Les Paul called it sound on sound. The idea was deceptively simple. You play a part, record it onto tape. Then you play the tape back through your headphones while simultaneously performing a second part, and you record both, the playback and the new performance. Onto a second machine. Now you've got 2 parts on one piece of tape. Rewind, do it again. 3 parts, 4, 8, 12. His 1948 recording, Lover, which honestly still sounds otherworldly if you hear it today, featured 8 layers of electric guitar, all played by Les Paul himself, built up through this painstaking process of overdubbing. Now, you already know the problem with this. because we talked about it with the Beatles. Every generation of copying adds noise. Every bounce degrades the signal. Les Paul was working with this limitation years before George Martin ever set foot in Abbey Road, and he was acutely aware of it. He'd spend hours getting a single layer right, because once you committed to it and recorded the next layer on top, there was no going back. That first layer was now embedded in the mix, permanently, with whatever imperfections it carried. If you made a mistake on layer 7, you didn't just lose layer 7. You lost everything, because all the previous layers were already mixed together on that tape. You'd have to start over from scratch. And Les Paul did start over, again and again and again. His wife and musical partner, Mary Ford, whose real name was Iris Colleen Summers, would sometimes record dozens of vocal takes for a single song, layering harmonies with herself, creating these lush, impossibly rich vocal arrangements that sounded like a full choir but were just one woman's voice, multiplied. Their hit, How High the Moon, from 1951, is a perfect example. If you listen to it, you hear what sounds like a whole ensemble, guitars cascading over each other, voices weaving in and out, and it's basically two people in a living room with some very clever tape machines. Here's what made Les Paul different from just a talented tinkerer. He understood, intuitively, something that the recording industry wouldn't fully grasp for another decade or two, that the studio itself was a creative instrument, that the act of recording wasn't just about faithfully capturing a performance, but about creating something new, something that existed only because of the recording process. Sound familiar? It's exactly what George Martin and the Beatles would realize in the mid-1960s. But Les Paul was there first, working it out with modified Ampex machines in the early 1950s. He actually approached Ampex directly and asked them to build him a machine with multiple recording heads, a true multi-track recorder, where different parts could be recorded on separate parallel tracks on the same piece of tape, each one independent, each one individually adjustable. Ampex built him a custom 8-track machine around 1957, and this was genuinely revolutionary. Because now, for the first time, you didn't have to mix everything together as you went. You could keep each layer separate. You could adjust the volume of the guitar without affecting the vocal. You could re-record just one part without destroying everything else. This is the architecture that all modern recording is built on. Every digital audio workstation you've ever heard of, Pro Tools, Logic, Ableton, GarageBand on your phone, is fundamentally a multi-track recorder. The concept is identical to what Les Paul asked Ampex to build him in the 1950s. The difference is that instead of parallel strips of magnetic tape running past recording heads, you've got parallel streams of numbers stored in memory, each one a discrete channel of audio data, and because they're numbers, all those problems that plagued Les Paul, the noise accumulation, the generational loss, the permanence of every decision, simply vanish. You can have 500 tracks, and the last one is exactly as clean as the first. You can move a note that was played a fraction of a second too late. You can change the pitch of a vocal without changing its speed. You can, if you want, take a mediocre performance and edit it into something that sounds flawless. And that last point is worth sitting with for a moment, because it raises a question that people in the music world have been arguing about for decades now. When you can fix anything, when the technology removes essentially all constraints, what happens to the music? There's a tool called Auto-Tune. You've probably heard of it, maybe heard people complain about it. It was invented by Andy Hildebrand, an electrical engineer who had previously worked for Exxon, using signal processing algorithms to interpret seismic data for oil exploration. In 1997, He realized that the same mathematical techniques, autocorrelation functions essentially, could be used to detect the pitch of a singing voice in real time and correct it. Nudge every note to the nearest semitone. Make every performance perfectly in tune. When Antares Audio Technologies released Auto-Tune in late 1997, it was designed as an invisible correction tool. Something you'd apply subtly, so the audience would never know. And then Cher's producers used it on her 1998 single Believe with the correction speed set to 0, meaning instantaneous, unnaturally fast pitch correction, and it created that distinctive, robotic, warbling vocal effect that became one of the defining sounds of late 1990s and 2000s pop music. What was designed to be invisible became an audible aesthetic choice. That's a pattern you see over and over in the history of sound technology. Tools designed for transparency get pushed until they become expressive. But the subtler use of auto-tune, the invisible kind, is far more widespread and far more interesting to think about. The vast majority of commercially released vocal recordings today have some degree of pitch correction applied. Not enough that you'd notice it as an effect, just enough to smooth out the small imperfections that every human voice naturally produces. And this connects back to something fundamental about how we perceive sound, something we talked about much earlier. The way your cochlea performs its own spectral analysis, the way your auditory system is remarkably sensitive to pitch relationships. We can detect pitch deviations of just a few cents, a cent being 1/100th of a semitone. That's an incredibly fine resolution. So when a singer is off by 15 or 20 cents on a note, some listeners will feel that something's slightly wrong even if they can't articulate what it is. Auto-tune cleans that up. Whether that's a good thing or a loss of something essentially human in music is a debate that doesn't have a clean answer. What's not debatable is that digital signal processing has transformed every aspect of how sound is created, captured, manipulated, and delivered. Think about noise cancellation, for instance. Those headphones you might wear on a plane. The principle is beautiful in its simplicity, and it's a direct application of something we covered early on: destructive interference. Remember, when two waves of the same frequency meet, and one is exactly half a wavelength out of phase with the other, they cancel. The peaks of one align with the troughs of the other, and you get silence. Noise-canceling headphones have tiny microphones on the outside that pick up ambient sound, the drone of the airplane engine, the rumble of the train, and a processor inside that analyzes that sound wave, generates an inverted copy of it, and plays that inverted copy through the headphone speakers along with your music. The ambient noise and its inverse cancel each other out, and what you're left with is dramatically reduced background noise. It's superposition, the same principle we talked about with Thomas Young's work, except now it's being computed in real time by a chip smaller than your fingernail. The processing power required to do this is genuinely remarkable when you think about it. The system has to sample the incoming noise, compute the inverse waveform, and output it all within a few milliseconds. Because if there's too much delay, the inverse wave won't align properly with the noise it's trying to cancel, and the whole thing falls apart. The latency budget is incredibly tight, and it has to do this continuously, adapting to changing noise conditions, thousands of times per second. The fact that this works at all is a testament to how far digital signal processing has come since Cooley and Tukey published their fast Fourier transform algorithm in 1965. And noise cancellation is just one example. Digital signal processing is everywhere in your daily experience of sound, often in ways you'd never think about. When you make a phone call, your voice is digitized, compressed using sophisticated codecs that model the characteristics of human speech. They know which frequencies carry the most information for intelligibility, which parts your ear and brain need, and which parts can be approximated and transmitted as packets of data. The codec on the other end reconstructs your voice from those packets. If a packet gets lost in transit, the algorithm interpolates, filling in the gap with its best guess based on what came before and after. You almost never notice. Your brain, combined with the algorithm, papers over the imperfections. Or think about the acoustics of the room you're in right now. If you've ever been on a video call from a room with hard walls and no furniture, a bathroom say, you know how terrible it sounds. All those reflections, all that reverberation, making your voice muddy and echoey. Modern conferencing software uses digital processing to analyze the reverberant characteristics of your room and actively suppress them, effectively performing in software what Wallace Sabine did with physical materials at Harvard over a century ago. The algorithm estimates the room's impulse response, how sound bounces around the space, and then filters it out, leaving your voice sounding cleaner and more direct than it actually is in the physical space you're sitting in. This idea of the impulse response is actually a beautiful concept, and it ties together so many threads of what we've been talking about. An impulse response is essentially the acoustic fingerprint of a space. If you could produce a perfect, infinitely short click, a single instantaneous burst of sound energy, and record what happens to it in a room, you'd capture every reflection, every absorption, every resonance, every delay. That recording is the impulse response. And here's what's mathematically elegant about it. Once you have a room's impulse response, you can use convolution, a mathematical operation closely related to the Fourier analysis we discussed, to predict exactly what any sound would sound like in that room. You can take a vocal recorded in a completely dead, silent studio, convolve it with the impulse response of Notre Dame Cathedral, and it will sound precisely as if that vocal had been performed inside Notre Dame. Every echo, every wash of reverberation, perfectly reproduced. Recording engineers actually do this. They travel to famous concert halls, churches, canyons, stairwells, any space with interesting acoustics, and capture impulse responses, usually by popping a balloon or firing a starter pistol and recording the result with high-quality microphones. Those impulse responses become tools, stored as audio files, that can be loaded into convolution reverb plugins in any digital audio workstation. So a producer working in a bedroom in Tokyo can make a recording sound like it was made in the Sydney Opera House, or in a specific room at Abbey Road Studios, or in a medieval stone chapel in rural France. The acoustics of physical spaces have been digitized, turned into data, made portable and reproducible. Wallace Sabine would have found this absolutely remarkable, because this is exactly what he spent his career trying to understand, the relationship between a room and the sound inside it. He measured it with stopwatches and organ pipes and his own ears, painstakingly cataloging how long it took for sound to die away in lecture halls and chapels. And now, over a century later, we can capture that same information in a fraction of a second, store it in a file smaller than a photograph, and apply it to any sound we want, anywhere in the world. The thing Sabine spent years quantifying with his reverberation equation, we can now reproduce with almost eerie precision, using nothing but math and a recording of a balloon pop. And that feels like a good place to start pulling some of these threads together, because if you've been drifting along with me through all of this, through Pythagoras and his hammers, through Newton's calculations, through Edison shouting into tin foil, through George Martin's splicing tape with a razor blade, through Nyquist's elegant sampling theorem. What you've really been hearing is one long story about humanity's relationship with something we can't see, can't touch, can't hold in our hands. Sound is invisible. It's transient. It exists only in the moment of its happening, and then it's gone. And yet we've spent thousands of years trying to understand it, capture it, shape it, and share it. Think about how extraordinary that impulse is. Of all the things early humans could have tried to figure out, and they had plenty of practical problems to solve, finding food, building shelter, staying alive, they also spent time thinking about why a plucked string sounds the way it does, why a cave echoes, why some combinations of notes feel harmonious and others feel dissonant. That curiosity isn't practical in any survival sense. It's something deeper. It's the same curiosity that drove Pythagoras to stretch strings across a wooden board and measure the ratios, that drove Helmholtz to build his resonators and press them against his ear one frequency at a time, that drove Fourier to insist that any complex wave could be decomposed into simple sine waves, even when the mathematicians of his day told him he was wrong. And here's what strikes me about the whole arc of this story. Every major breakthrough in our understanding of sound has come from someone noticing a connection between things that seemed unrelated. Pythagoras connected music to mathematics. Helmholtz connected physics to physiology. Sabine connected architecture to acoustic measurement. Nyquist connected the continuous world of analog signals to the discrete world of digital samples. Hildebrand connected petroleum engineering to pitch correction. Over and over, the advances came not from specialists digging deeper into their own narrow field, but from someone who had one foot in two different worlds and noticed that the same patterns kept showing up. That's actually one of the most beautiful things about sound as a subject. It sits at this intersection of so many disciplines. Physics, obviously, sound is mechanical wave propagation, and you can describe it with equations of motion and pressure differentials and all the tools of classical mechanics. But it's also biology, because the way your ear works, the way your cochlea performs its own real-time frequency analysis, is one of the most sophisticated pieces of biological engineering in the natural world. It's mathematics, because Fourier analysis and convolution and sampling theory are deep, elegant mathematical ideas that happen to describe acoustic phenomena perfectly. It's materials science, because the speed of sound depends on the density and elasticity of whatever medium it's traveling through, and the acoustic properties of a concert hall depend on whether the walls are plaster or wood or glass. It's psychology, because the way you perceive sound, what sounds pleasant, what sounds frightening, what sounds like music versus noise, is shaped by your brain, your culture, your memories, your expectations. Two people can hear the exact same pressure wave and have completely different experiences of it. And it's history. That's maybe what I've enjoyed most about this journey we've taken together. The history of sound is the history of human ingenuity, full of real people making real choices, sometimes brilliant, sometimes stubborn, sometimes just lucky. Think about Edouard Léon Scott de Martinville, who built a machine that could record sound 20 years before Edison, but never thought to play it back. Think about Emile Berliner, who looked at Edison's cylinder and thought, no, a flat disc makes more sense, and was right in a way that shaped the entire music industry for a century. Think about Les Paul, a kid from Waukesha, Wisconsin, who stuck a phonograph needle into his guitar and heard the future. Think about Bing Crosby writing a check to invest in a tape machine because he didn't want to do live radio anymore, and accidentally funding the technology that would transform recording forever. These stories matter because they remind us that technology doesn't just happen. It's not inevitable. It's the result of specific people, in specific circumstances, making specific decisions. And those decisions are shaped by everything: by economics, by war, by ego, by accident, by the simple human desire to hear a sound one more time after it's faded away. Let's sit with that desire for a moment, because I think it's actually the emotional core of this whole subject. Why did Edison build the phonograph? The practical applications he imagined were things like dictation and telephone messages. But the thing that captured the world's imagination was something simpler and more profound. You could hear a voice that wasn't there. You could hear a person who had left the room, or left the city, or, eventually, left the world entirely. Recording is, at its heart, a way of making the ephemeral permanent. Sound, which by its nature exists only in the present tense, suddenly had a past tense. You could play it again. You could hear it tomorrow. You could hear it 100 years from now. And we do. We have recordings of people who died over a century ago. We can hear Enrico Caruso singing, his voice captured on wax in the early 1900s, preserved through all the format changes, transferred from cylinder to disc to tape to digital file, and still recognizable, still moving, still unmistakably human. The pressure waves that left his vocal cords in a recording studio in Camden, New Jersey, in 1904 were transduced into grooves in wax, and those grooves were copied and distributed and eventually digitized, and now they exist as ones and zeros on servers all over the world, and when you press play, those ones and zeros are converted back into electrical signals, and those electrical signals drive a speaker cone back and forth, and that speaker cone pushes air molecules, and those air molecules reach your eardrum, and your eardrum vibrates, and your ossicles amplify the vibration, and your cochlea performs its frequency analysis, and your auditory nerve fires, and your brain assembles the signal into the perception of a human voice singing an aria from Pagliacci. The chain of transduction is extraordinary. From vocal cords to air to wax to groove to electrical signal to magnetic pattern to digital sample to electrical signal to speaker to air to eardrum to nerve impulse to conscious experience. Every link in that chain is a feat of engineering, and every link depends on the same fundamental physics we've been talking about all night. That chain is getting longer and more sophisticated all the time, but the endpoints haven't changed. It still starts with something vibrating, a voice, an instrument, a hand clapping, a door closing. And it still ends with your ear and your brain doing what they've been doing for hundreds of thousands of years. All the technology in between is just our way of extending the reach of sound beyond its natural limits, beyond the walls of the room, beyond the moment of its creation, beyond the lifetime of the person who made it. And now, in the age we're living in, sound has become so thoroughly digitized, so completely woven into the fabric of daily life, that it's almost invisible. You wake up, and your phone alarm plays a sound that was designed by an audio engineer, processed through a tiny digital-to-analog converter, and pushed out through a speaker smaller than a coin. You talk to a voice assistant that uses speech recognition algorithms, descendants of Fourier analysis, to parse your words into meaning. You put in earbuds that use active noise cancellation, real-time destructive interference, computed thousands of times per second, to subtract the sound of the world around you. You listen to music that was recorded in a studio, mixed on a digital audio workstation, mastered with algorithms, compressed into a streaming format that uses psychoacoustic models of your hearing to decide which parts of the sound you won't miss and delivered to your ears over the internet as a stream of data packets. You make a phone call, and your voice is sampled, quantized, compressed by a speech codec, broken into packets, sent across a network, reassembled, decoded, converted back to analog, and played through a speaker, pressed against someone else's ear, all with so little delay that you can have a natural conversation. Every single one of those steps involves principles we've talked about tonight. And here's what I find quietly astonishing about all of it. Despite the extraordinary complexity of the technology, the experience of hearing remains fundamentally the same as it's always been. When you listen to a beautiful piece of music, your cochlea doesn't care whether the sound waves came from a live orchestra or a streaming service. Your brain doesn't experience the math. You just hear music. You feel something. The emotional response to sound. The way a minor chord can make you melancholy. The way a sudden loud noise can make your heart race. The way a familiar voice can make you feel safe. That's ancient. That's pre-language. That's wired into the deepest parts of what it means to be a human animal on this planet. Sound was here before we were. Wind through trees, water over rocks, thunder rolling across a plain. The physics of pressure waves propagating through a medium didn't wait for us to discover them. They were operating when the first creatures developed the ability to sense vibrations hundreds of millions of years ago, long before anything like an ear existed. The ear itself is an evolutionary marvel. This improbable chain of membrane and bone and fluid and hair cells that converts mechanical energy into electrical signals with a sensitivity and dynamic range that still humbles the best microphones we can build. Your ear can detect vibrations of the eardrum smaller than the diameter of a hydrogen atom. It can handle sounds 1 trillion times more intense than the quietest thing it can hear. It can distinguish thousands of different frequencies simultaneously, in real time, without any conscious effort on your part. It's been doing this your whole life, every waking moment, and even while you sleep, processing the acoustic world around you, keeping you oriented, keeping you connected, keeping you alive. So as you lie here, wherever you are, whatever time it is, whatever kind of day you've had, your ears are still working. They're picking up the ambient sound of your room, the hum of an appliance maybe, the distant murmur of traffic or wind or rain or silence. Those sounds are pressure waves, just like the ones Pythagoras studied, just like the ones Newton calculated the speed of, just like the ones Sabine measured in lecture halls, just like the ones Edison scratched into tin foil. The physics hasn't changed. The air molecules around you are doing exactly what air molecules have always done, bumping into each other, passing energy along, carrying information from source to ear at roughly 343 meters per second. And your brain is doing what brains do. It's taking all that information, all those frequencies and amplitudes and timing differences between your two ears, and it's building a picture of the world. Not a visual picture, an acoustic one. A sense of space, of distance, of presence. You know how big your room is, partly because of how sound behaves in it. You know whether a sound is close or far, partly because of how the air absorbs high frequencies over distance. You know whether you're indoors or outdoors, partly because of the pattern of reflections your brain has learned to interpret without you ever thinking about it. That's the thing about sound. It's always there. It's the sense you can't turn off, the one that works in the dark, the one that works around corners, the one that wakes you from sleep when something isn't right. It connects you to the world in a way that's so constant and so fundamental that you mostly don't notice it. The way you don't notice gravity until you think about it. But now you've thought about it. You've spent this time learning about the physics and the history and the engineering and the people. And maybe some of it will stick, and maybe some of it will have drifted past you like sound itself, here for a moment, and then gone. And that's perfectly fine. Because the beautiful thing about understanding is that even a little of it changes how you experience the world. The next time you hear an echo, you might think about reflection and absorption. The next time you hear a choir in a cathedral, you might think about reverberation time and Sabine's equation. The next time you put on headphones, you might think about Nyquist and sampling rates and the long chain of transduction that brings music from a studio to your ears. Or you might not think about any of it. You might just listen and feel and let the sound wash over you the way it always has, the way it did for every human who ever lived, the way it will for every human who ever will. The air around you is full of vibrations right now, some too faint to hear, some at frequencies beyond the range of your perception, all of them real, all of them following the same laws of physics that have governed the universe since long before there was anyone around to listen. And your ears, those extraordinary, improbable, beautiful instruments, are translating those vibrations into experience, into meaning, into the feeling of being here, in this moment, in this room, alive and listening. So let that be enough. Let the sound of whatever's around you be what it is, just air molecules, doing what they do, carrying the world to you one gentle wave at a time. And if sleep is close, let it come. You've followed the story of sound from ancient Greece to the digital age, from vibrating strings to streaming audio, from a philosopher with a hammer to an engineer with a laptop. It's been a long, winding, fascinating road, and the road goes on. There's always more to learn, always another layer to peel back, always another connection waiting to be noticed. But for now, this is a good place to rest. The sound will still be there in the morning, doing what it's always done, waiting for you to listen.